Just a few minutes. I'm checking on the other one. But good afternoon, everyone. It's my great pleasure to have here today Professor Burak Kantarci. Burak, thank you so much for accepting the invitation to deliver this talk inside the ACM Distinguished Lecture. Professor Kantarci will talk about AI-backed security and resilience for cyber physical systems. He is associate professor and the founding director of the Next Generation Communications and Computing Networks, NextCon Research Lab, and the Smart Connected Vehicles Innovation Center at the University of Ottawa. So I will give the floor for Professor introduce better himself. But again, thank you so much, Burak. It's a pleasure to have you here.
Thank you very much, Michelle, for the warm introduction. It's a great pleasure to be here, although virtually. And thank you very much for the invitation. I'm very pleased to be here and delivering this talk today as a part of the seminar series in your department, the data science and cybersecurity seminar series, I suppose, and also the ACM Distinguished Speaker as a part of the ACM Distinguished Speaker program. I'm assuming everyone can see my screen right now. Yes. All right. Awesome. Thank you very much. Now I can also see on the other screen as well. So the title of today's talk is going to be AI-backed security and resilience for cyber physical systems. And as I said, the talk is actually part of your seminar series and also the ACM Distinguished Speaker Program. And as Professor Nogueira introduced, I'm actually with the School of Electrical Engineering and Computer Science at the University of Ottawa, and I'm the founding director of NextCon and SCVI labs. I'm going to talk about these labs actually and what we're doing in these labs in the context of data science and also cybersecurity in both topics in a few minutes. But before that, as a part of my mandate, I also need to talk about ACM, which is the Association for Computing Machinery, and it's actually the largest organization for computing professionals, as you all know, and it operates in more than 170 countries, and it has over 2 million members connected through ACM, and it helps solve the problems in computing in the future by bringing computing professionals and academics, as well as researchers and students together. And I'm a proud member of ACM, and I encourage you to become a member if you're not yet. So, and the ESP program has been made actually possible by ACM, as you know, and you can see the link here for more information about this program. And as I was saying, I was introducing myself as the founding director of the NextCon and SCVI labs. I had initially started this in 2014 when I was at Clarkson University, and I was so happy to also host Michelle there in 2015, as far as I remember. So that's where I started NextCon lab. But when I moved to the University of Ottawa, I built actually the lab, NextCon lab there. And in 2020, we received support from Canada Foundation and Foundation for Innovation to build the first academic research lab in Canada's largest technopark in the west end of Ottawa, which we call Kanata North. So we're going to have actually a soft launch event on the 25th, which really makes me very excited these days. So we are moving there outside the main campus. And what we have been doing and what we're going to be doing in SCVI center as well. Well, we are focusing on cyber physical systems, and the main focus is, of course, is going to be smart and connected vehicles, or Internet of Vehicles in general. And our vision is connected and autonomous vehicles for smart cities. So what we are focusing on in our research is safety and non-safety applications. And of course, we're dealing with big sense data and some relevant problems regarding the big sense data. And we're also seeing the vehicles, connected vehicles, as the nodes in an environment where we leverage multi-access edge computing. And of course, these are individual users that provide that push data to the network. So this is actually from one of our previous works regarding our vision, how the vehicles of these cyber physical systems can be integrated into a smart city infrastructure. And what else we are doing is, this is another interesting area that we've been working. So connected autonomous vehicles working or serving for first responders to be able to save labor costs and to be able to also make more accurate decisions. And as you know, whenever there is an accident, we report the accident, and by law, we need actually all three first responders there, including the police, the ambulance, and also the firefighters. But depending on the accident scene, we might be able to say which set of first responders are needed. So this is actually one of our previous works, by using deep learning models to crowdsource the dashcam images from accident scenes. And depending on the severity of those accident scenes, we are deciding which set of first responders or which specific first responder is needed there. And of course, energy decentralization is another use case here of Internet of Vehicles. When we have, of course, electric vehicles, we can use electric vehicles as means of energy storage and, of course, energy sources, in other words. So the problems that we are dealing here is actually multifold, it's twofold in general. And one of them is the operational aspects, how to ensure that the energy needs are satisfied and the utilities are maximized. And of course, the other aspect is the communication related aspect in an environment where we have microgrids that aim to sustain their own energy. And we also have electric vehicles that are integrated into that environment. Another area that we are working on is, of course, the sensor fusion in a vehicular sensing environment. So basically, the machine learning backed characterization of the sensor signals in vehicles. So this is not actually detecting anomalous driving events. What we are doing, we are trying to characterize those events. The challenge here is those anomalous events are rare. So they are not actually too many that your machine learning models can learn from. So you need some additional solutions to be able to train your system accordingly and to be able to make accurate decisions regarding those rare events. So we have developed actually some solutions against those. That was actually a project supported by Ontario Centres of Excellence, or the new name Ontario Centre of Innovation. And what we are also doing is we are continuing to work on this topic, and also we are developing some security and safety solutions for connected and autonomous vehicles. And we're also working on some UAV assisted services, like integration of UAVs into the aerial and terrestrial network systems, where UAVs can serve as base stations or aerial base stations. And of course, very recently we have worked on integrating the connected and autonomous vehicles to in order to resolve the pandemic crisis where we can use them as rapid testing centers by detecting some vulnerable areas, and by deploying these vehicles in those areas and trying to find out the risk scores of these regions, and to have these vehicles circulate around those regions and bring the tests to the patients instead of calling the patients to the tests. So in an environment where we have IoT devices, we expect the communities to be smart, connected, and secure. Now, as you can see here, the use cases are various, just like detecting the road conditions here, like a pothole detection or a tree fall detection or a car accident detection, as you can see here. Well, we can use the same systems for public safety. You see actually an active shooter here in this example. So in the case of an emergency, how do you inform the people and how do you direct the people towards safe locations? So, and how do you, of course, again, this has two aspects. There's one operational aspect here to optimize the decisions. The other aspect is, the other challenge is how to communicate this. There are communication-related aspects, how to communicate this in a fast, efficient, and a secure manner to the end users. Okay, and that's why this smart mobility, smart living, and public safety aspects, when we leverage IoT systems, they take us to smart, connected, and secure communities. So this is actually a very recent use case where we used crowdsense data to be able to cope with the pandemic crisis. And as you can see here, the data is coming from the public transportation data or the transit data. And once this is pre-processed, we can obtain a social contact network. And depending on the social contact network, we can obtain a risk map of the region that we are monitoring. And depending on that, we can deploy these connected vehicles that can bring the tests to the patients. And at the same time, we can also make optimum decisions for the supply chain systems. Because what we have learned during this pandemic is that our supply chains are really fragile. So we need also robust decision support systems to be able to make our supply chains stronger. And that was actually a project that we have recently completed. And another aspect is actually the ubiquitous sensing for smart cities. As you can see, initially this had started with the support of National Science Foundation when I was with Clarkson University, and then I started another project. I started another project with the support of NSERC, which is Natural Sciences and Engineering Research Council of Canada. So the good thing about the ubiquitous sensing systems, or more general, I use the term crowdsensing system very liberally to denote all of these ubiquitous sensing systems or devices. This is actually non-dedicated. This is a non-dedicated sensing system, so you don't have any upfront commitment. You can tap into the existing resources if you need data, sense data in an environment, as you can see here. Of course, this brings you the flexibility, and it's a low-cost solution. You don't need to deploy extra sensors. You can eliminate the high capital expenditures, as well as the operational expenses. You don't need to maintain that system because you just get the service from the sensor. The sensor is not actually is beyond being a piece of hardware. The sensor is actually a service. It becomes a service. So we can also leverage the mobile edge computing for data services in such an architecture. These are all the good points, but the downsides of this is, of course, there's privacy leakage. So you might be using someone's smartphone data, or you might be using someone's vehicle's data, or someone's wearables data. So there's privacy leakage. And since this data is collected and transmitted to a central server for potential decision-making service, there might be data poisoning attacks on that environment to be able to poison the model that will be trained. So data poisoning is another threat here. And of course, clogging, that's how I generalize this sort of threat here in this environment. Clogging attacks are other types of attacks. We can actually make an analogy to the DOS attacks in a networked environment. So the ultimate goal of DOS attacks, as you know, is to make the resources unavailable by flooding those requests. The same idea here. The sensing service sensing requests here made to these devices can also have the same aim: to clog the system, to drain the battery power, to utilize the communication resources, computing resources, storage resources, as well as the energy resources in these devices, sensing devices. So it is possible. So these are the downsides of this type of system. So we need intelligent security solutions. That's what we are developing here. And what we are focusing on in terms of IoT sensing and cybersecurity, as you can see here, we actually need some intelligent gaming solutions against data poisoning attacks or false sensing data publishing attempts. I'm going to talk about this in a few minutes in more detail. You're going to see that. And of course, we need to know if that particular device is in possession of the right person. So, while the traditional methods can be used, certainly, like passwords, PIN codes, or even hard biometrics, but they may not be feasible in a real-time environment where we require data from these devices in continuous manner. So we need to, of course, leverage behavioral biometrics to come up with behavioral user profiles, and we need to identify these users continuously. And in the case of a spoofing attempt, we can identify this by leveraging some intelligent mechanisms. That's what we have also developed in our lab. Context is, of course, an important dimension here for continuous authentication or continuous access control. Now, context-aware authentication or context-aware access control, that's another area that we have been working on, because when you make decisions, when you make authorization decisions or access control decisions, you need to also take into account the context of the user. Now, let me give you an example, because this is going to be also context-aware access control or risk-aware access control I'm going to be talking about in this talk, but context is actually an integral part of that. Now, I can give you an example for this. If you're in an office environment and you're using your, let's say, your mobile device, let's say your tablet or your laptop, well, that environment, the risk in that environment is not the same as the risk in an environment that you have outsiders. If you're working in a coffee shop, well, you have outsiders, and you might be working on sensitive data when you work with your device. Even if you are behind a VPN, well, your screen might be displaying some sensitive information. So your context is not the same as your context when you work in your office environment. And it may change, it may vary. Even in the same location, it may vary depending on who is around you. So context is actually an important dimension when you make access control or authorization decisions. So I'll be talking about this, and we have also developed solutions against the threats in such situations, in high-risk situations. And I talked about the clogging attacks a few minutes ago or seconds ago in a ubiquitous sensing environment. We need actually some intelligent methods or models to be able to anticipate these type of attacks, like clogging attacks, for instance. The clogging attacks aim to drain the battery power, drain the utilize, consume the computing power or storage power or communication resources in these type of devices in such an environment. So we don't have enough data. We don't have open data for that, but we need to understand the nature of these attacks. And there actually we have a strong tool like adversarial machine learning. I'll also talk about that. But besides that, the traditional machine learning tools can also be used to model and to anticipate the impact of such attacks. So when you are able to model that type of attacks, you of course need strong and robust schemes to defend against that type of attacks. So that takes us to the AI-based detection of various types of attacks in a ubiquitous sensing environment. Now, I'm going to take you from the attack surfaces. I'll start with the attack surfaces in IoT networks or IIoT networks. And I'll take you to the network layer issues, the security issues, or detecting intrusive patterns in the network layer in IoT environment. And I'll take you to the application layer in a cyber physical system. And then we'll talk about the threats in a ubiquitous sensing environment, in a crowd sensing environment, the security issues there. So let's start with the attack surfaces in IoT networks or in an IIoT networks, industrial IoT systems. As you can see here, we have the remote site where the control systems and the system management system management facilities reside, and the information that flows from the control systems, which is actually in the form of a raw network traffic, it gets aggregated with the structured data through the control system management unit, okay? And the remote site data service feeds this data into our enterprise location, okay? So here, this is the first point of entry. So that's where your cybersecurity event detection is going to occur. So we have the management processes, patches, and logs here, okay? The asset data here goes into your dashboard, and then it goes to the analyst's PC. Now, the attacks here in such an environment can be considered under hard to detect under two categories. That's how I categorize them. So one category is the attack types that we've been working on for a good amount of time, which can be relatively easily detected, or which are more detectable, and which takes lesser time to pursue and to succeed in. And the other type of attacks take longer time, just like the advanced persistent threat attacks, because they need some more time to collect the information and to understand the dynamics of the system and to pursue the attack. So there are several types of APT attacks, of course. Just three of them that we are focusing on are the pivoting, lateral movement, and data exfiltration. So they target the analyst machines with the ultimate goal of exfiltrating data from these machines. So what they basically do is actually they just, after the first point of entry, they laterally move towards that target by pivoting towards that direction. Now, this is how the data looks like. So this is actually our in-house generated data. As you can see, we have normal traffic to lateral movement, reconnaissance to data exfiltration, pivoting, and initial compromise type of attacks here. And what you can see here is this is actually a data, as I said before, that we generated in our lab environment. And this is the data that we use to train our machine learning models. Now, as you can see in this graph, vast majority of the data consists of normal traffic patterns, as expected, all right? And what you can see is just a little bit of pivoting attacks here. This is actually a 2D representation after plotting via TSNE, T-distributed stochastic neighbor embedding, okay? And you can see these clusters of different types of patterns here, and very rare initial compromise and data exfiltration events here. Now, when we want to test our model, okay, if you want to train our model, this is what we have. If you want to test our model, again, the situation is more or less similar, but not very much alike, of course. The vast majority is still, as you can see, the normal traffic. We don't have too many attack patterns here. So the first challenge that we need to deal with is this rarity problem regarding these, with respect to these attack types. Okay, so we don't have too many of these attack types. So the situation is beyond the imbalance problem. Okay, so there's actually, the problem is the rarity problem. It's beyond the data set being imbalanced. So we can use several tools for that. Very recently, actually, we have used some autoencoders and also some adversarial models to be able to cope with this, and some oversampling methods can certainly help with that. But definitely, there's no one works for all recipe that you can use in any environment here. Okay. Now, a challenge here when you work with IoT or IIoT environment is actually the availability of open data sets. In one of our recent works, we generated actually a data set for different types of data, not the APT attacks, of course. So this was actually built based on the NSL KDD data set, but we just simulated IoT networks that consists of IoT objects that use Kantarci NG operating systems. So we generated these attacks and made, of course, the traces available if you're interested. And what you can see in that environment is, as you see, of course, in this figure, the number of samples that we had, the vast majority is normal. We have IP sweep, LANSP, ping of death, Smurf, SYN flood, port scanning, and UDP flood attacks. And what we see here in this particular work was, okay, XGBoost was the most superior technique to detect this these attacks in this environment. When we tested the same algorithms, the same classifiers in different contexts, just like the example that I was talking about, the APT attacks, for instance, or when you have different types of attacks, and when the generation of those attacks are more rare, then you actually have a problem here. So you can't say that, okay, XGBoost is going to be the most superior scheme here to detect all of these attack types. We can't say that, because there are certain cases where AdaBoost will make decisions that are better when you have one type of attack. Okay. There are some cases where random forest can outperform XGBoost, and there are some attack types where XGBoost makes better decisions. So it's not easy to say that we can come up with a single classifier that will outperform the rest of the classifiers when you have different types of attack patterns. So what do we need? Well, we need ensemble decisions. Okay. So we need to come up with new ensemble methods. And this is what we have proposed for that. So, and this work actually is going to appear in IEEE GlobeCon proceedings at the end of this year in December 2021. So as I said before, we have a number of machine learning models that can be superior and that can outperform the other machine learning models under certain types of attacks. So the indicator here can be any of these performance parameters, but just to make life easier for everyone, I can say that, well, if you use the F-score as the indicator to make this decision, well, it's going to give you the best performance or best indication to be able to make your ensemble decision. So why do we need the F-score? Okay, we look at the F-scores of these different machine learning models, and we sort them with respect to their best number of F1 scores. What do I mean by that? Well, if XGBoost gives you 5 best F1 scores for out of, let's say, 10 different attack types, okay, so the score of XGBoost is 5. If AdaBoost gives you 4 best F1 scores for the rest, then AdaBoost is going to be your next best classifier. If random forest gives you the best decision for just 1 out of this 10 attack types, we can't discard that because every attack leads to a damage cost and a response cost if you're able to detect, of course. So that's why even one of these machine learning models, if they make some good decisions, even for a single type of attack, we can't discard that. We have to take that into our ensemble decision. Now, in that example that I was just giving to you, I said XGBoost makes 5 best decisions in terms of F-scores for these attack types, and AdaBoost makes 4 best decisions in terms of these attack scores. All right, so I get AdaBoost and XGBoost as my first front runners in the first step, and now I have an aggregation model. So if, let's assume XGBoost says that, well, this type of attack is a DOS attack, and if XGBoost is making the best decision in terms of the F-scores for DOS patterns, I'm going to rely on XGBoost. If AdaBoost says that, okay, this is actually a remote to local, an R2L attack, and let's assume AdaBoost gives me the best F1 score for R2L. Okay, AdaBoost is going to be the trusted model for me. Well, if none of them can tell me whether this is a U2R attack, user to root, now I can't make a final decision for that. I need to wait for the model that will give me the best decision for the U2R attack. Okay, so this will loop over again. Okay, and here I will have my own aggregated model that will become my first machine learning model in that case. And I'm going to bring, what was I saying? Let's say random forest. So random forest is going to be my next front runner here. Okay, now I can rely on random forest for U2R. So if it says this is U2R, I'm going to rely on random forest's decision. Okay, until I can cover all types of attacks, I'm going to loop over here and I'm going to bring new models. So that's how the ensemble model is going to work here. Okay, and that's our scheme, our approach to boost the accuracy, okay, the overall accuracy in such an environment. Now, I'm moving towards the application level or system and application level, considering a cyber physical settings. So this is based on a number of works that you see here that I'm referencing. These are the selected works, of course. We have a cyber physical setting. In the cyber physical setting, this is actually an emergency room in a hospital environment. So we have people coming into this room, and we have doctors, we have nurses, we have some other hospital staff in the same environment. We have patients or maybe some visitors in that environment. So the context is not always the same here. So we can't give them authorization for the same action type in two different times in the same place, because context is important. So we need to understand couplings. What do I mean by couplings? Couplings is actually how often or how frequent, not or actually, and or. How often and or how frequent two people are co-located. How often and or how long a device and a person are together. So these are the couplings, okay? And these make our context. So with these couplings, we obtain some clusters, okay? And within every single cluster, we look at the risk level of that cluster, depending on every single data point in that cluster. A data point is actually an action. An action is like a read attempt or a write attempt into a file. Okay, but we need to understand the context. We need to understand the situation. Who are co-located there and which location we're talking about. How often do they get co-located? Okay, and this is actually what we call the couplings. Now, we also have some probability-based risk levels to be able to label these clusters that will help us tell whether this is a high-risk cluster, this is a medium-risk cluster or a low-risk cluster. And this will help us improve our security policy. Okay, so this will generate a security report, but a human written policy will use this information to improve itself. And how does that happen? This is how we define this. We have a number of people in this setting. This is, as I said, a cyber physical setting. We have sensors collecting this information and providing inputs to us. We have some assets, some digital assets, which we call the documents here that we want to access. We have some devices. We have different locations in this medical environment. Okay, now every event consists of an object set here. So a person, a device, and a document or an asset. Okay, and that object set, of course, occurs in a location at a certain time. So this is an event. So the events actually occur sequentially in time, and we obtain these cyber physical features, which we call the couplings. So location to device, or document to device, or location to document, document to people, device to people. So when we say coupling, we look at the duration, okay, how long they get co-located, or how often do they get co-located. So it can be time-based or frequency-based coupling, or we can use both of them in our cyber physical feature definitions. Okay. Now, when we use these combined features, time-based and frequency-based, when the security policy, the human written, based on the domain experts, when the policy permitted an action, our clustering-based decision permitted that action by labeling those clusters as medium risk clusters. Okay. And as you can see here, our permit decisions comply with the actual policy by 100%. And when the policy denied an action, as you can see here, we're missing a small amount, but our deny decision with the high risk label complies with the policy more than 99%, as you can see here. Okay, and this is actually a breakdown of these decisions. So the policy permits, and we have low, medium, and high risk clusters here, and these are the ones that we permitted, and these are the ones, as you can see, that were denied by the policy, and this is what we ended up allowing. Okay, so there's still some room for improvement here, but what we can say is we actually came up with useful inputs for the human written policy on how to incorporate the risk levels in an automated manner. Okay, now moving from the application and the system level towards the crowd-sensed data and its trustworthiness. Now, what do I mean by trustworthiness? This is how I define the trustworthiness of big crowd-sensed data. I define these 4 pieces of a puzzle. So there's a challenge about recruiting the devices. The devices are owned by users here. I'm talking about smartphones, wearables, or vehicles, or tablets. But these devices are in possession of real users. So we need to get these users on board, and we need to recruit them. So how to recruit these users and their devices, in other words, effectively, that's one problem, one piece of the problem. And of course, there's going to be some Sybil-like attempts in such an environment. How do we detect that type of behavior? And how can we empower game theoretic solutions to be able to improve the trustworthiness of such a system? That's the third piece of the puzzle. How can we formulate a game between the crowd sensing platform, the center platform, and the participants? By participants, I mean the device owners. So that's the third piece of the puzzle. And of course, if there's a clogging attack or attempt against the system, how do we detect that? The clogging attack is going to be in the form of fake tasks. So there's going to be real tasks that we really want that information. I want to know the traffic intensity in that environment, or I want to know what the crowd in a certain location is doing, or where they are moving towards, or what the current situation of the crowd is. But while I'm dealing with such an important task, if someone is submitting some task request that will keep the system busy, we need to find a mechanism to eliminate those type of tasks, okay, and not to submit them into this environment. And as you can see, where do we use this ubiquitous sensing systems? There are various use cases, as you can see. We can use them in emergency preparedness. I just gave an example about evacuation or crowd monitoring. Another use case can be environment monitoring, or we can use the systems in healthcare and well-being, as well as indoor localization or even navigation systems, or public safety, and several other use cases, as you can see here in this figure. The question here will become how to capitalize on these devices. Now, this is actually an integral component of the big data phenomenon that we've been dealing with for the last decade and even more than that. So we're dealing with, at the beginning, we had started with 3 V's actually, where we were talking about the volume, velocity, and variety. Now we're actually talking about 5 dimensions of the big data, where we additionally have the veracity and the value. By value, we literally mean the value of the data, which is said to be the field of the next decade. Now, the question here becomes how to capitalize on these devices when we handle data out of these smart devices. So the first piece of the puzzle that I presented to you, this is actually an auction-driven user recruitment. So the users here, they send their locations and of course the costs of sensing. And they can publish this in a sensing, the data publishing layer. Social networking applications is just here for illustration. It can be anything, any environment in a platform, but it's actually very handy to use to communicate with these sensing data providers. Well, when the end user submits a task to the central platform, a sensing task, the platform is going to get the information about who is available to provide this data. So we know which users are available and what their sensing costs are. Okay, we're going to select the users and we're going to place their rewards because, as I said, we need to capitalize on these devices. Nothing is free. We're using their resources, and we need to compensate the data owners or the device owners. Okay, so we need to reward them. All right, users have been selected and payments have been placed, and we receive the data and provide the final decision or final service to the end user. Well, this is fine, but when we say trustworthiness of this data, well, the trustworthiness is actually a problem where we may have users that join this auction with lower bids, okay? And as soon as they get selected, they're going to send false data to spread disinformation. And as you know, if somebody is providing a service at a lower cost, this is something that sounds reasonable, that sounds more feasible. So they are more likely to get selected, unless you have a mechanism against that type of an action. Okay, so the initial solution here is to maintain a reputation database. So when we are selecting the sensors, every sensor or every user who is in possession of that sensor is assigned an initial reputation, and as they provide data, we update their reputations. And how do we update the reputations? We look at their positive readings and negative readings. What do I mean by positive and negative here? Well, positive means that if your reading is not an outlier, because if I'm monitoring a crowd and if I need acceleration data, let's say, well, I'm not getting that service from a single user. I'm getting that service from a number of users. If I need acceleration data and I need voice, sound data, and I need some images maybe, okay? So this is actually multidimensional data that's not a single sensor, okay? So I'm getting that service from multiple users. So if your reading is marked as an outlier, it's actually a negative reading. Otherwise, it's a positive reading. So your positive readings to your total readings, that's your instantaneous reputation in a single campaign. Now, of course, as time elapses and as you get selected more, your reputation is going to get updated on a running average basis. Okay. And if your negative readings are more than your positive readings, of course, your reputation is going to drop down and it's going to affect your, it's going to decrease your likelihood to be selected in the next rounds. Okay. And of course, you won't be making any rewards out of this. to be able to detect the Sybil-like actions here, we don't need to reinvent the wheel. So we can adopt and adapt an existing mechanism that is already used in social networks. So everybody in a community can vote for the trustworthiness of another user. As you can see here, we have user 0, okay, arriving in community 1, and everyone else in that community is voting for the trustworthiness of this user. So this is actually a more decentralized solution compared to the previous approach. Now, what forms a community can be a question here. Well, if two devices have at least one sensing task in common, they become a part of the same community. And as soon as a new device joins a new community, everyone else casts a vote for the trustworthiness of this user. And of course, this is not a very democratic system. Not everybody has the same weight for their vote, okay? And the one who gets voted gets a vote weight as the average of the weights of the vote capacities of the other voters who votes for them, okay? So the vote capacity of this user can be 1, vote capacity of this user can be 0.7, vote capacity of this user can be 0.8. And of course, they also have their reputations as well. So what we basically do is we use their vote capacities as well as their reputation and their votes. And of course, this is normalized by the total vote capacity and the reputation, which gives us the instantaneous reputation for this new user. And when this user joins another community at another time, well, we use the previous reputation, we assign it some weight, and we get a new instantaneous reputation here, but the overall weighted sum gives us the overall trustworthiness score of this new user. So this actually, as I said, it's not reinventing the wheel, it's adopting an existing mechanism that detects the social network Sybil users. So we are adapting it to the crowdsensing environment. And what is the basis for voting for the trustworthiness of someone as a negative or a positive vote here is basically based on some certain similarity scores of your sensor readings. Okay, now how can we merge these two approaches to ensure that we don't get anyone malicious on board? Okay, here we define a game theoretic approach. Here we formulate a repeated subgame. Now we ask the users to collaborate with the platform. At the beginning, we have the user recruitment phase. So here we recruit the users based on that reputation awareness scheme or based on fully decentralized decision that can be based on the votes of the community. Doesn't matter. But we have a recruitment phase. We know with whom we are dealing. Okay? And we also have a predetermined here calculated rewards for these users. In the second phase, we invite the users to participate in this game. And what is that game? The game is actually to vote for the trustworthiness of the other users in your community. Now, how do you do that? You look at the similarity scores, okay? And based on the similarity score, you cast a negative or positive vote. And at the end of the voting stage, if your vote turns out to be helpful for the platform, you are categorized under the high award category, plus your reputation and vote capacity gets improved, and your initially determined reward gets improved here as well. If your vote turns out to be not useful for the platform, well, you're going to lose your initially determined reward, as you can see here, because you're going to be categorized under low award category, and you're going to use your vote capacity here. In the second stage, it's not mandatory to participate in this game. So every user makes a strategy here on whether or not to participate in this collaborative decision-making phase. You may choose not to participate, or you may choose to participate and possibly to increase your reward. But if your vote turns out to be not helpful for the platform, you are in the low award category. What do I mean by not helpful for the platform? Well, if you cast a positive vote for someone who is actually who turns out to be an adversary, you're not helpful for the platform. It doesn't matter whether it's intentional or whether you are cooperating with the other user, but your vote is not helpful for the platform. It doesn't help. If you're voting positive for a cooperative user, or if you vote negative for an adversary, that is actually a helpful vote, and that makes you be categorized under the high award category, and that makes you get an increased vote capacity in the third stage. So this is how we formulate this. And at the end, as you can see here, Sonata, I had to actually mention this is a social network assisted trustworthiness assurance in that environment, so which is purely based on decentralized votes, is compared to the first stage. We have statistical reputation, and then we have the sub-game perfect equilibrium based decision. And when we start with the vote-based reputation, what we see here is basically in terms of the platforms and the users or devices utilities. Well, if we start with the statistical reputation, which is followed by the game formulation, the sub-game formulation, well, we can improve the user utility and the platform utility as we have more tasks to arrive, more sensing tasks to arrive to this community. But more importantly, what we can see here is we don't reward the malicious users at all, as opposed to what Sonata does. So we can ensure better platform utility, we can increase the user utility, and we avoid paying to the malicious users. Now, there's a last piece of this puzzle, which is going to be the last thing that I'm going to be talking about, the clogging behavior in this environment, the clogging attacks. This is actually a twofold problem, as I said before, because we don't have enough data to understand the nature of these attack types. So we need actually an AI-backed modeling of these types of attacks. And of course, we need AI-backed detection. So we can use artificial intelligence for both aims. Now, when we say fake tasks, those tasks can start from a certain point and they can move out of a certain zone. Every task actually has a range, by the way. So you deploy the task, let's say in this location, and I want information from the users within the range of this task. So you put the circle here, so anyone who is within the circle is going to report me. So the tasks can actually move, the subtasks of this task can move out of the circle, and they can come back in. Okay, the red ones are the clogging tasks. The blue ones are actually the normal tasks. So this is what we call the zone-free movement of these tasks. Another possibility can be the aim of highest possible damage to the system. So the fake tasks are concentrated in a particular region, as you can see here. So this is what we call the zone-limited movement of these fake tasks. So we need to investigate both scenarios here. Now, what we did against this is we actually trained a self-organizing feature map here to place these tasks optimally on the map of the cities that we monitored. Okay. And of course, what other features make up these tasks? I'm going to be talking about that. It's not only the location. Maybe it's better to first talk about those features, and then we'll get back to the impact and how this works. So these are the features that make up a task. So the location, the time, the duration of a task, how long you need them to sense. And of course, the residual time of this task, the subtasks, will actually give us the residual time, the resources that they need, the coverage of the task, and whether or not this is during the on-peak hour. And we actually partition the monitored city into multiple grids, so the grid number. So these are actually the features. So how do we optimally come up with fake tasks to place them on the map and to give the ultimate possible damage? How can we anticipate this? So when we trained our SOM, self-organizing feature map, and when we collected the results, this is how it looks like, by the way. As you can see, it's not easy to distinguish the legitimate and fake tasks from each other. We just color-coded them when we put the 2D TSNE mappings of these tasks. So our anticipated tasks, the red ones, are very much, those clusters are very much alike and together with the legitimate tasks. And what is the actual impact of this on the system? Well, when the tasks move in a zone-free movement manner or a zone-limited manner, it's more or less the same under different self-organizing feature map configurations. Okay, so the initial configurations you can see here. Okay, what we can see in this figure is up to 1/3 of the entire energy consumption in this system can be consumed and drained by these fake tasks that are deployed by an AI-backed backbone. Now, the question here is, how can we detect the fake tasks? Okay, we actually can empower some ensemble learning mechanisms here. And as you know, ensemble learning, I just made a brief introduction to it. We have a number of weak learners, and they make a decision, an aggregated decision, which will take us to a strong learner, as you can see here in this example. So this is actually our methodology. What you can see here is the test and train results. The boosting algorithms are tested for almost a week, for 6 days, as you can see here. The gentle boost can lead to the best accuracy, as you can see in this figure, but there's no feature selection here. Okay, so when we use feature selection, okay, when we select the most important features here, that can further help us improve the accuracy of our decision in the detection of fake tasks, as you can see in this figure. Okay, so we were somewhere around 93 point something or 94%, so we can go up to 96% accuracy at the end of the 6 day. Now, to conclude, well, if we empower machine learning based intrusion detection, we can certainly improve the accuracy of our intrusion detection models. And what can be actually a promising solution in this context is ensemble learning, as I said before. So we can use multiple weak learners to come up with some strong learners. And also to be able to make access control or authorization decisions in cyber-physical settings, we can use some risk-aware models, and we can make it even finer grained. I just talked about low, medium, and high risk levels, but we can make it even finer grained, and that can improve the security policies of organizations. For the big crowd-sense data, if we want to deal with false sensing tasks, we can empower game theoretic solutions, as you have seen, and we can empower artificial intelligence empowered adversarial models to assess the impact of potential clogging attacks or fake task submissions in this settings. And if we, of course, want to rely on machine machine learning models and basically the boosting models, we can achieve more than 95% accuracy in the detection of these tasks. When we move forward, what else? What other opportunities do we have? Very recently, actually, we presented another anticipation model for poisoning attacks in mobile crowd sensing settings, where we, of course, again, leveraged competitive learning. Another possibility here is empowering knowledge-based models. So in our recent works, we have also introduced some prior knowledge input-based models to boost the accuracy of what I have shown here in our ensemble model. So that 95, 96% can even go to 97, 98, even actually 99% in the most recent works. We have seen that. That can help. And we can also use this type of trustworthiness assurance approaches in other contexts like connected vehicles, as you can see here. And we actually need open data sets for pursuing research in this area. And definitely deep learning solutions can complement, can further improve as needed, improve the performance of detecting intrusive patterns as needed. And of course, if you want to anticipate the mobile crowd sensing systems more robust, and if you want to anticipate the threats actually of the crowd sensing systems, we can, of course, leverage some adversarial models. So in less than a week, I'll be presenting our recent work on how to use adversarial machine learning to anticipate the fake tasks in a mobile crowd sensing environment. So this actually concludes the talk. Thank you very much. A big thank you for listening. I'm happy to answer any questions. I'm not doing all of these things by myself, so I'm working with a number of researchers. So this is a screenshot from our website for all the people who have participated in or have contributed to the research in Nextcon and IoT labs. We even actually have 2 visiting researchers, and both of them leveraged the visiting researcher program at the University of Ottawa. One of them was also from Brazil and co-supervised between Professor Nogueira and myself, as you can also see in this slide. Well, thank you very much. I'm happy to answer any of your questions.
Thank you so much, Burak. Indeed, we have a question. When you were on slide 14, we had a question regarding to. So Daniela, I will put here on the screen. So is this a TSNE reduction of dimension? So she asked over slide 14.
Is this slide?
Is 14. Yeah.
Is this okay? It's this one. Yes, exactly. So TSNE can be used for exactly reducing the dimensions. Yeah. So we map this
I
onto
think
2
it was
dimensions.
in the beginning.
Map our data onto. Yeah, but this one is also a TSNE plot as well. So
I see.
Yeah, same idea.
Okay. Yeah, so now we have more questions here. One is from, I will start, is from Leandro Souza. He says, considering the importance of data in order to ensure reliable detection, like the example you mentioned about the recognition of crisis situation, critical situations such as accidents and supply chain interruption, are there steps being taken by the industry in order to make such data ready, really available and consistent between different vendors, cyber physical systems?
This is a very good question, actually. The works that I presented, especially the ones that were related to the risk-aware decision, it was actually in collaboration with an industry partner. So the data that we used was not actually a simulated. It was actually a simulated data. It was synthetic data, but it was the data that was mimicking the actual data that our industry partner had. So with that, out of that collaboration, we actually had a patent filed with our industry partner. So it was actually a realistic environment in a medical setting, the risk-aware decision. For the supply chain part, I actually described one of the projects at the beginning. It wasn't hardly tied to the security aspects, but it was more about resolving the pandemic crisis. But we definitely also have an industry partner in that project as well, where we worked on using open data to provide these services and decision support systems to supply chains or to any decision makers when needed.
I was checking your slide 21. My question is regarding to, you said you have used it, if I understood well, you have used time-based and frequency-based features. Is that the case?
Yes.
So how
that's correct.
Can you I didn't take exactly maybe the idea that you had.
Yeah, sure. I'm happy to elaborate on that. This was actually a very exciting part of that research project. We collaborated with our industry partner earlier for context-aware authorization. This was about risk-aware access control decisions. Now, what we mean by this is, consider an emergency room at a hospital. Okay, so you have a patient there, and that patient gets coupled with another person, which can be a doctor, which can be a nurse, or another non-medical staff in the hospital. Okay.
So couple here means some kind of relationship or some relation between two entities.
Co-location. Yes, in that example, exactly. So a doctor uses a device, but a nurse can use the same device as well to enter data, to access some data, to access the same document, but they may not have the same privileges. Okay, but that device can occur in that room, in the room of that patient. Okay, so that is the location to device coupling. And how often that coupling occurs is this, and how long that coupling has occurred is this. Next time it occurs is, of course, another event for that coupling, for location to device coupling. For document to device coupling, again, we access that digital asset from this device. That is, again, a coupling. And how often do we work on that asset is the frequency. How long do we spend time on that asset is, of course, it makes another feature in that environment. So that's how we generate the event sequences and the couplings. We extract the couplings out of those event sequences in that cyber physical setting.
So, but in this case, do you use some sort of machine learning or classification to separate this? And I don't know if this is really the idea, but
the idea here is you don't need machine learning to detect the couplings because it's just the data processing stage. But where machine learning kicks in is the step where we obtain the clusters of these couplings. Now, when you plot the clusters of these of every action, every event, you see some of them accumulate together, and some of those data points in a certain cluster, they may denote high risk actions, but of course, based on some probabilistic calculations, we obtain the risk level of the entire cluster. So you get assigned, that data point gets assigned the risk level of that cluster at the end. So where machine learning kicks in is the point where we want to obtain those clusters. So basically, unsupervised learning is leveraged there.
I see. We have some comments here on the chat. We have Fernando. He says, great talk. Thank you, Professor. If I understand correctly, the resilience in collecting information is based on the concept of crowdsensing. But I imagine that in some areas, population concentration or time of sensing can affect the amount of data and consequently the applications that benefit from it.
Mm-hmm.
Another point he says is another question, even considering the time of collecting, transmitting, and processing data, can this type of scheme be employed in real-time or mission-critical applications?
Now, let me start with the first question. Thank you for the questions, Fernando. It definitely affects the location that you're monitoring. In our studies, actually, we focused on multiple locations. So we presented our results in different cities, in a small city, in a big city, which was a more crowded one, which was highly populated. So we analyzed also the impact of that one, these contexts as well. One important point maybe I should have mentioned is the aim for the adversaries in generating this type of fake tasks is to maximize the impact, the damage on the system. And what do I mean by that? Well, whenever it is the on-peak time, most of these tasks are aimed to be submitted during on-peak times. And they tend to, of course, target more users, more populated areas. So we look at the mobility patterns of these users as well when we train our self-organizing feature map in that particular study. So we look at the mobility patterns and we look at the mobility of the users at different times of the days. And of course, these tasks aim for different resources. They tend to last longer, but of course, they tend to disguise themselves. And that's why how we want to, that's how we train our model, so to make them sort of disguise themselves from the legitimate tasks. But we do analyze the impact of that. Now, for the second question, in real-time mission-critical applications, can this be used? Of course, it depends on what sort of mission-critical applications we are talking about. If we are talking about some military applications, it is definitely debatable. I don't want to get into that discussion. But if we are talking about public safety, for instance, like crowd monitoring, for crowd monitoring, crowd sensing is already being considered to be used, and there are some case studies on how crowd sensing can be used for public safety applications, certainly for civilian applications, I mean.
Thank you, Burak. We have last question here is from Bruno. He says, as I understood, some applications that you have mentioned use network graphs information. Is this correct? If yes, he has a second question.
Some applications use network or graph information. They can use, yes, but the network information that I talk about is actually the network flows. So I didn't actually mention the graphs there. So it wasn't network graphs, the information regarding the topology. Okay, in other words, so it wasn't about topological information. It was the features that we extract from the flows.
Okay, so it's not the case, but I will read his second question just to see if it makes sense for you. He says graph neural networks models can beat some traditional ML classifiers like RF in some fields like NLP. Do you think that GCN can be applied in your works?
It can be definitely a possibility. So that was a part of our internal discussions, actually. So we haven't applied, but it's definitely in our radar.
Burak, thank you so much for your for having accepted our invitation. It was really a pleasure. Of course, as you mentioned, we have already some collaborations. And if anyone attending this seminar is interested to collaborate with us, can contact me, and then we can work together and make some kind of bridge to you also and collaborate with. Thank you so much.
Thank you very much, Michelle. The pleasure is mine. It was a great pleasure. Sorry, I think I overused my time, but I really appreciate. I enjoyed the discussions and talking to this audience. Thank you very much. Thanks a lot.
Thank you. Bye.
Bye.
Tchau a todos. Bom, obrigada.